titled Tracing the Events at Norochchole. What happens after a blackout occurs in a large thermal power plant. So many enthusiastic participants have already joined our webinar today, and we hope to serve you well. This EMF will be conducted by Mr. Nirmal Undungoda. Mr. Undungoda is the operation engineer of the Lakvijaya Power Plant, Norochchole. Mr. Undungoda obtained his degree in electrical engineering from the University of Moratuwa in 2014 and subsequently joined the Ceylon Electricity Board in 2015 and was promoted to the Lakvijaya Power Plant. He has over 9 years experience as an operation engineer in the power plant. Without further ado, I take pleasure in inviting Mr. Undungoda to conduct his presentation. Audience, if you do have any questions in the meantime, please direct your questions via the chat box. Mr. Undungoda, the floor is unto you, sir, to conduct the presentation. Thank you.
Thank you, Ms. Nimasha. Good evening to all the SLIMA members and the distinguished members of the community. Thank you for the opportunity given by Sri Lanka Energy Managers Association to explain the situation that occurred during the course of the blackout in Norochchole Power Plant. Now, please hold on while I share my screen. Now, so there are many misconceptions and misinformations is being circulated about what caused the blackout and why there were load shedding even after the blackout occurred and why Norochchole can't resume its operation soon after the blackout. Now, to get to that point, first we have to look at from the perspective of the power plant and of course from the grid perspective as well. Now, first, we will look briefly about what happened in the perspective of the grid. Now, you see, in a healthy power system, your demand and supply is balanced at 50 Hertz. Now, when the demand is lower, of course, the weight of the demand is lower, your generation it is in excess. So, your frequency gets higher. So, to get the system back to its original operation condition, you have to curtail the generation. Now, and then if the demand is high and the generation is lower, that means that the frequency will get lower, so that for some reason, if the generation kept on getting low, the frequency will go further down. So this is the basic principle of frequency, and either of these extreme ends are not good for any generator. So if the grid kept going on to the safety limits, those generators will trip themselves to avoid damage to their maybe transformer or generator assembly. Now, in order to know about the blackout condition in the thermal power plant, of course, we will have to get insight about the internal operation of the power plant. Now, any steam-driven power plant, steam-driven thermal power plant, almost all over the world, uses the Rankine cycle to operate. Now, let me briefly explain about the Rankine cycle. Now, you see in stage 1, stage 1, you have a fluid. The fluid, of course, it's water. Now, water is being pumped. So, you get high pressure water here. Now, this high pressure water is being fed to a boiler. Now, the boiler, inside the boiler, you boil the water and get steam, and further the steam gets heat from the coal, and you get, at the end of the boiler, you get high pressure, high temperature mixture of dry steam. Now, that high pressure, high temperature steam is being fed to the turbine, which comes in contact with the turbine blades and rotates the turbine. The turbine blades mounted on the shaft. At the end of the shaft, you have a coupled generator which generates electricity. Now, the exhaust of the turbine is still at steam phase. Now, in order to be used in the cycle, in order to complete the cycle, you have to have to have condensed water. Now, this condensation is done by the condenser. Now, the condenser takes out or ejects latent heat of this steam. And so finally the cycle completes and water is ready to be pumped again through the cycle. Now, this is what happens in the Rankine cycle very briefly. Now, I will briefly explain the major equipment that are being used in each phase. Now, and what are their parameters and their properties. Now, these items will later contribute to our blackout explanation. Now, the first stage is the pumping cycle or pumping phase. As the name implies, there are pumps in this phase. Out of these pumps, the boiler feed pump, as the name implies, feeds water to the boiler. Now, there are 3 boiler feed pumps in each unit, and which uses 2 of them during the running condition, of course, in the full load condition. Now, each electric driven pump has a capacity of 5 megawatts and is capable of feeding a more than 500 tons per hour at a pressure of 17 megapascals. Now, since it's quite large, it's a major equipment in the power plant, which is supplied by the 6 kV auxiliary station supply. Now, since the pump is quite large, the assembly of the pump and the motor is quite heavy. So, your bearings need to be lubricated properly, and the lubrication has to be cooled properly. So, we have a separate lubrication oil station. Cooling is there, filtering is there to circulating lubrication oil throughout the operation of this boiler feed pump, and it draws a very large current, of course. Now, because of this current, the winding gets pretty heated up very fast. Now, because of that, you have to cool the windings as well. Now, to cater all the cooling requirements throughout the power plant, we have a separate auxiliary system, circulating cooling water, the cycle cooling water pump, which has a 400 kilowatt rating, and another cycle pump with 250 kilowatt cooling pump. So all these apparatus has to work prior to starting of this boiler feed pump. These are essential auxiliaries which are also being powered by the 6 kV station supply. Now, all these things has to be there in order to work this pump. Now, let's move on to the boiling phase. Now, in the boiling phase, it involves in pipes, tubes that run through the furnace, getting energy from the burnt coal and, of course, from the flue gas. Now, in the middle, you have an specific equipment known as the steam drum. The steam drum stores steam generated from water tubes and of course, acts as an phase separator. So, this is where the steam and water separation occurs. Now, this 189 ton, 19 meters long, 17 centimeters thick pressure vessel holds about 23 tons of water during the operation at a pressure of 16.5 megapascal, 165 bars, at a temperature of 350 degrees of Celsius. Now, since the water inside the steam drum is at 350 degrees, your structure, the metal temperature of the steam drum is also at 350 degrees. Now the manufacturer, if you want to fill the empty boiler, empty steam drum, the feeding temperature, the temperature difference of steam drum and the feeding water has to be less than 50 degrees. So that means if the steam drum metal temperature is 350 degrees, the feeding water temperature has to be at least of 300 degrees. Now, this is to avoid damage to the steam drum by uneven expansion. It's just like this. Now, when let's say when your car radiator is hot, and somehow if you manage to lose its water. Now, in the radiator, if you want to fill the radiator again in order to run the car, you have to fill the radiator with water. Now, you have to wait until the radiator cools down in order to protect the radiator, and otherwise the weldings and joints will get cracked. So the same thing applies to the steam drum as well. Now, but for the purpose of cooling down, this is where the problem comes. It takes about 4 to 5 days because the shear structure of the steam drum. Now, this is also because the temperature that we can achieve of the pumping phase is of about 120 to 150 degrees of Celsius unless the boiler is being fired. Okay. So when the steam is not available from the firing is not available in the boiler, the pumping temperature that we can achieve is about 130 degrees of Celsius from the use of auxiliary boiler. Right? So you can see here the steam drum metal temperature is being carefully monitored in the power plant. You can see there are many points in the steam drum which is taken. So this is an actual picture of the control room diagrams of the Norochchole power plant. Then let's move into the turbine phase. Now, high pressure steam and high temperature, high pressure steam comes into the turbine and exits the LP turbine. Now, there are 3 phases: high pressure, intermediate pressure, and low pressure. For the sake of ease, let's treat them as a one single entity. Now, if we will be able to get maximum amount of work done from this turbine if you can keep the highest enthalpy difference at the ends. So across the turbine, if you manage to keep the highest enthalpy difference, you will get maximum work done from the turbine, so that per cycle you can get maximum energy out of it. So essentially that means this is the highest pressure point that we can achieve, and this is the lowest pressure and temperature points. So in fact, this place is at vacuum pressure. Now, so this is some sort of a image of a turbine. Now you can see this is the end of the LP turbine. Now LP turbine is, because of that, is designed to cater that sort of very low pressures. So on below that you have the condenser also. The condenser also is designed to cater very low pressures. So if somehow you manage to overpressure these places, there is something called a rupture disk here, or the diaphragm valve. Now this diaphragm valve is a passive equipment which bursts itself if it detects a high pressure situation. So simply it will burst itself, allowing exhaustion of pressurized steam in the LP turbine or the condenser downstream. Right. Now finally, the condenser. Now the LP turbine exhaust of the condenser comes on top of the condenser. So steam inlets comes to the condenser from the top portion. Now there are 16,000 tubes, about 16,000 tubes in the condenser. Now inside this tube, you have cooling water flowing. Now when the steam gets in contact with these tubes, what it does is it takes out the latent heat of the steam and condenses the steam into water. Now the water is being dropped to the bottom and ready to be used once again in the pump itself. Now this cooling water is taken by from Indian Ocean, of course. Now this is pumped from a 2 megawatt pumps. Of course, because of this is quite large, it has its own motor cooling system and lubrication oil system, gland sealing, all the things working in perfect condition in order to run this pumps. So its own auxiliaries has to be there if you want to run the pumps. Right. Now all these equipments in each phase, to put them into operation, first we have to achieve their working conditions and do preliminary requirements also. Now in the case of pumps, now of course you have to do arrange few things prior to the startup. Now the pumps, simply you have to make sure the suction lines are fully open and suction fluid is available. And of course, sometimes the discharge must be controlled. Sometimes it has to be closed. Sometimes you will control it, open it slightly according to the situation. And most importantly, if it is a centrifugal pump, of course, you have to prime the pump, vent the line, fill the line full of liquid. Otherwise, to avoid, otherwise, if air pockets is remained when you start the pump, your line will get hammered and sometimes it will broke out. And then, of course, you have to protect the pump impellers from eroding. So the pump priming is quite important. And of course, as I've told you, in the case of BFP, boiler feed pump, the pump and drive bearing has to be lubricated. The lubrication oil system has to run. Prior to the starting, the mechanical seals has to be set properly. Now, and of course, the cooling water pumps, it has to work. Cooling water pumps, cooling apparatus has to work prior to the startup. Otherwise, your windings, your lubrication oil get heated up very quickly and it will be bad to the do more damage than the startup. And of course, achieve water chemistry. So if there is a requirement, you have to achieve the water chemistry. Maybe sometimes you have to start the filters beforehand. And of course, in the case of steam drum and turbine, of course, you have to control the steam and water admission so that you can control the temperature inside the drum, the turbine, so that there is no uneven expansion. Now, so that you can avoid damages to lines and connections. Now the real issue here is that in reality, there's a long list of items that need to be accomplished before starting up any large equipment. Now the same preliminaries, the prior actions does applies when you stop a pump or that particular equipment. Now you can't just restart it in just a flip of a switch. All these activities has to be done or even rechecked or achieved, or else you may end up with damaging or sometimes maybe destroying that valuable equipment, so that rendering them unavailable for weeks or maybe even months. So that is very bad, because those valuable equipment are quite, it takes time to repair them. Right. So that's why we can't directly start those particular auxiliaries if they are being stopped abruptly. Now, that is about the Rankine cycle and the equipment in a general thermal power plant. Now, to talk about a sudden trip of the power plant, so let's just say for some reason the power plant gets tripped. Now, this is an extension of the same Rankine cycle. You can see it's nothing more than the included in the coal supply and the boiler here. So you have the condenser, the boiler feed pump, just set of pumps here feeding the boiler. And of course, here you have the steam drum here as well. It's not shown here. And of course, steam is being directed to the turbine, and the turbine rotates. In the same shaft, you have the generator here. And then the exhaust of the turbine goes directly into the condenser. Of course, cooling water is there. It cools down. And the terminals of the generator is connected to the transformer, and via the transformer it connects to the grid, the transmission line. This 300 megawatt generator is now being connected via the generator circuit breaker here to the transmission line from 220,000 volts. Now, for some reason, when you trip the power plant, and of course, tell you something in advance, there is an energy transfer here. Now, see, the chemical energy of the coal supply comes to the boiler. The chemical energy here transfers to the combustion energy, and the combustion energy is being taken to the steam line. Now, the energy of the steam goes to the turbine, which converts to mechanical energy, and the mechanical energy is being transferred to the electricity here. Now, this electricity is directly goes to the grid. Now, there is a smooth energy transfer here. Now, what happens is that if you manage to trip the plant for some reason, automatically or otherwise, what happens is that this energy generated here will get stuck here. Now, in order to avoid the turbine getting overspeed, you have to close the governor valves here. Now, many equipment inside the turbine as well, you have some sort of an residual steam left. So those steam will be directly dumped to the condenser. Of course, even though you stop the coal supply here, some sort of a residual energy will remain in the furnace and of course in the steam line. So when you close the steam turbine governor valves, what happens is that this line will get overpressurized, or else sometimes all the steam lines needs to dumped into the condenser. Now this condensation, so what you do is this happens almost automatically. Those excess steam, not only from the steam line, comes to the condenser, and now what we have is we still have this supply of water, the main cooling water pumps providing water to the condenser. Now this water flow is there so that this dumped steam can be converted to or condensed into water. And of course, this boiler feed pump is available and all its auxiliaries are available so that you can safely fill the steam drum very quickly, so that there will be no temperature difference amongst the fed water and the steam drum metal temperature. Now, both these pumps are grid supply. So that is what happens during a normal tripping of the power plant. Now, in the blackout, what happens is that even though when the power plant opens this generator circuit breaker, you won't have power to the 6 kV equipment, or these two pumps and all of their auxiliaries will lose power, so that you have no choice but to stop these pumps from working condition. So grid supply will not be available. This cooling water pump will not be available. So cooling water flowing to the condenser will not be available. That means the steam will get trapped here and the pressure will increase here. Now this pressure, as I've told you earlier, there is an diaphragm valve here, a rupture disc. A diaphragm disc is available here, which if the condenser and LP turbine gets overpressurized, it will burst out and steam will be exhausted. So to protect the LP turbine and condenser. Furthermore, you will not have these two pumps and water flowing will not be there, and simply the steam drum will starve from water, so that you won't have any more water inside the steam drum. All the water up to here will get evaporated. Now, so in order to resume operations, you have to close this rupture disc or replace it. Now, it's very hard to replace this one because simply there is more steam is being pumped out. Steam is being exhausted here, so that you cannot reach this particular place without getting to safety limit. So it takes about 2 to 3 days minimum to reach this place to replace this ruptured diaphragm. Now I have prepared some sort of a video for you, so you can look at how the ruptured disc exhaustion happens during a blackout. So I think you will this presentation will play itself. Wait. This is how it's taken out. Right. You can see the shear strength of the steam exhaustion. See here. Okay. Okay. Now switching to house load. Now there is another option of if the grid failure occurs from a high frequency situation, only from a high frequency situation, of course, the generator can switch itself to house load operations when the generator circuit breaker opens. Now, this is not possible in under frequency situations. Now here, what happens is that the dying generator can provide power to these two pumps. Actually, what happens is that the system will not notice any sort of a disruption to station 6 kV auxiliary supply, so that all the auxiliary equipment, the cooling water pumps, lubrication oil pumps, all these things will work, will never notice a power disruption. Now, so the unit will continue running with its own auxiliaries and can be synchronized back to the grid. Now, what you can see, what you have to understand is when you operate this, if you want to take this unit into house load mode, essentially your connection to the grid is severe. Now that means that the generator will go into, now it has been generating 300 megawatts. Now only these two pumps and other auxiliaries will work. Now it's about 15 megawatts. Now it's some sort of almost, so that's a 5% from the rated generating value. So that's some sort of an almost full load rejection So the OEM recommends that the plant should not operate in house load for more than 30 minutes. That means during the 30 minutes of operation, so if you manage to operate this plant in house load for 30 minutes, the OEM does not recommend keeping it longer than that, and you have to reconnect it to the grid by resynchronizing it. So of course, you can see here, and you have to keep the boiler fire lit so that the steam supply is there, very low steam supply is there. Now, of course, you have to use this bypass duct as well to control the steam lines, pressure, temperature, all these things. Now, this exercise is quite very unstable. Now, this cause very extremely unstable behaviors to plant and every equipment, maybe leading to hazards, vibrations, damages. So there's only a handful of times we have operated in house loads. Of course, it's as per the OEM, it's not recommended to operate in house load. Now, unfortunately, in the situation of under frequency of the grid, definitely the units has to be tripped, rendering all the 6 kV auxiliary power loss. So in an under frequency situation, these two items and their auxiliaries will trip. Now, therefore, both the rupture disk and the drum starving will occur, rupture disk failure. Hence, the tripped units will have no choice but to wait until necessary equipment cools down. So 4-5 days has to be waited. Now in a point of view from the grid also, this confirms. Now you can see that this is an under frequency situation. I see here frequency is lower, high demand, low generation. Now if you try to take the unit from here, if you try to take the unit into house load mode, what happens is that you will take out this generation, making the supply side more lighter, or going further into low generation, so that ultimately the grid will lose its valuable generation, and of course the system will slide down to failure, imminent blackout during the under frequency. Now this is what happens during the blackout in a large thermal power plant. So however, in each unit, of course, to another note, each unit is equipped with a 630 kVA standby emergency diesel generator and a DC and UPS system to secure essential loads such as lubrication of our turbine, hydrogen sealing, and other important control systems, so that to avoid catastrophic damage. So that's the end of the presentation, and I hope that you have got the idea about why Norochchole can't resume its operation. So when it loses auxiliary power system, the 6 kV auxiliary power system. So, okay. Now, I will try to answer now it's, I think, the time for the Q&A session, and I will try my best to answer all to your queries. Of course, to an extent, I can answer, and to my knowledge, even. Thank you for listening.
Mr. Undungoda, thank you very much for the very insightful and timely presentation. In fact, we have almost 100 participants online, which actually testifies to the importance of the topic you discussed today. So in this context, I believe that the audience too would have very interesting questions. So please direct your questions to the chat box, or alternatively, you could raise your hand. And this Q&A session will be moderated by past President Mr. Harsha Wickramasinghe. Mr. Wickramasinghe, I hand it over to you to conduct the Q&A session.
Thank you, Nimashi. So I see there are so many experienced engineers here in the audience. And first chance goes to Mr. Parakrama Jayasinghe. Let me unmute you. Yes, you can speak now.
Yeah. As you expect, Harsha, I'll be the first to come. Now, actually, Mr. Undungoda, thank you very much for a very detailed explanation. So, there is no, what shall I say, bugs in it. You did it very, very well. But from our side, from outside, the question comes in because this is not the first time this happened to Norochchole. Hasn't anybody given any thought? Now, the whole problem is that, like you mentioned in the under-frequency situation, it trips and you have to wait for it to cool down, rupture discourse. All
Yes.
that is to be expected because those are safety measures. But particularly for Sri Lanka, Norochchole being such a major plant, we can't afford to do that. So has anybody given any thought, like you mentioned, that over frequency you can run it on the house load, but that is way too small a load. So is there any other way this could run? I mean, have any thought been given to that?
Now, what you suggest is going into house load operation during even in the course of under frequency situation, right? Am I correct? Hello, can you hear me? Hello?
Sorry, as far as we are concerned, the consumer, we can't afford the plant to go into that mode of rupture is going and 4 days of idleness.
Yes.
So what is the way to prevent that happening? If you say house load alone is not adequate for you to run for long enough, there must be some other means. Isn't there any discussion going on? How can we make sure it doesn't go into that mode, and so that we can bring it back to online as soon as possible?
Now the
I'm
problem
saying, yeah.
yes. Now the problem in here is that, of course, what you can do is you can start the cooling water pumps and all those auxiliaries.
Yes.
Now, yes. Now there has been solutions and solutions are looked into, but I think rather than their technical nature, of course, financing those solutions has been a challenge. I think has been a challenge, and of course, things are being looked at because, quite frankly, by using some other means other than the 6 kV auxiliary supply, it's we are unable to sort of start those pumps. Now you can see that I have in the presentation itself, I have told you that now prior to starting up these things, you have to take care of all the pumping mechanisms. Now
Yeah.
mechanical engineers should know this. Now
Yeah.
you have to do these preliminary activities. Otherwise, you will lose not only the rupture disc, but also that pump as well. Now, that is a very dangerous situation because that will take around more than the time spent on that blackout itself. Now things are being carefully looked at, but the solutions are there, of course. But realizing the solution is sort of a technical challenge, and more than that, financing those solutions is somewhat challenging.
No, but wouldn't you say our losing Norochchole for 4 days is big enough a burden that should be avoided? And also the way I'm looking now, recently I think the chairman suggested that they are going to buy a 30 megawatt auxiliary diesel power plant. Now, having 30 megawatts, you needed only about 15 megawatts, right? So that is not good.
I'm sorry, sir. That's per unit.
Per unit. Okay. Whatever it is.
Unit,
right?
Now,
so still it will be in that 5% range, no? So it still will be consuming only about 5% of the capacity. That's what the OEM does not want you to run for too long. So there's some missing component here. What is being done in other countries? I mean, are they also having the same problem?
Actually, I think in other countries, they do not have this problem. They have enough adequate spinning reserves to be run so that you won't have any sort of disruption to supply. Now, I can't say about their own grid and how their composition of generation occurred. But the problem here is, of course, you can't provide those supplies without damaging these equipments. So you have to provide solutions. So things are being looked at, and of course, the some sort of an auxiliary power system or diesel generators are going to be installed, but as you can see, starting up those equipment is quite heavy. Now these equipment, now let's say a 5 megawatt pump. Now it's a big pump. When you start a pump, even with let's say 30 megawatt diesel generator, when you simply close it, that means it will draw a very large inrush current and the
Yeah.
starting current will be
Yeah.
very high. Now, when that happens, now intermediately you have to propose some startup mechanism as well, starting methods as well. Now, that starting method has to be matched with pump's mechanical curves, mechanical properties. Now, some pumps won't even start without a set of, let's say, it has to start working at least from 50% speed. Now, those are very, very
Yeah. Thank you,
quite
Mr.
technical challenges.
I don't want to
These
pressure
things are
you.
being, yeah. Now, these things are being looked at, of course. Now, a solution is underway. Now, and of course, financing and these things are being looked at. So, very near future,
Thank you.
we
Thank you
hope
very
that
much.
finally we will be able to get out from this situation. Hopefully.
Thank you.
Nirmal,
Thank
there are
you.
some questions in the Q&A box also. Mr. Rukshan Jayasinghe, Kalum Pereira, Udara Gunasekara. So please go through them and try to answer. Can you access the Q&A box?
Yes, please wait.
Most of the questions raised in the Q&A box are probably answered by Nirmal during Mr. Parakrama Jayasinghe's question, but you can try to answer quickly the other questions as well. Can you see the questions?
I think, wait. I have it. This way. Yes, I have it. Is any PRVs actuated method can be replaced? No, the simple problem is that if you need to replace the diaphragm rupture disc, the steam flow the exhaustion of steam has to be stopped. Otherwise, if you replace it again, still there will be pressurizing in the LP turbine and it will fail again. Now, yes, it's universal for all plants to survive in our house load only in high frequency rate. So now,
Mr. Undungoda, sorry for the
yes.
interruption. Could you please read the question in whole and then answer, because the questions
Yes.
may not be visible to the audience. Thanks.
Now, I think the second question, what are the solutions associated with this situation, is being answered. Am I right?
Yes, I think you answered it.
Yes. Is it universal for all power plants to survive in house load only in the high frequency trip? Yes, of course. Apart from that, house load operation can work in even when the generator circuit breaker opens itself. For some other reason, let's say, not of course to internal to the power plants. Of course, if there's a generator failure in the generator, of course you can't work with the house load operation, right? So basically only in high frequency trip, and of course df by dt as well, rate of change of frequency in the high side. Is there any quick response mechanism to reconnection of grid at least one of the 300 megawatts after blackout? Now, reconnection is only possible if there is a blackout, now if you manage to somehow run the cooling water pumps to the boiler feed pumps and main cooling water pumps in the condenser and associated all auxiliary equipment, of course you can reconnect your unit after filling out. Of course, now of course the normal hot startup has to be carried out. Now it still takes some time because now you have to start from the zero, right? So it takes time to start the power plant, even if you manage to trip the power plant. So you can't get 300 megawatt right away. So you have to start low, maybe from 15 megawatts. So you reconnect it and then slowly keep on adding coal to the boiler and reach those temperatures required. And then finally you can achieve 300 megawatts. Can't we use the frequency control for the plant? Now, this frequency controlling from the plant is not that much available because now you see the chemical energy of the coal is being provided to the boiler. Now, from the boiler, it takes a considerable amount of time, about 8 to 10 minutes to reach that energy to the generator. Now you have to heat up the flue gas, get the steam out, water needs to be boiled, and then that steam has to reach the superheaters, sort of all parts, and then go through all the heating has to be done. So when you introduce coal, the pressure won't change. So that means that the fuel change will only be visible after 8 minutes. So that's why basically, even in the tripping itself, there is a big residual energy in the power plant. So unfortunately, frequency controlling is not possible for the power plant because the fuel control cannot be done and the fuel get stuck in there. What
Nirmal,
lessons
just
has been yes.
Mr. Noel Fonseca, he has raised his hand. Mr. Fonseca, you can speak up if you are there. Mr. Noel Fonseca?
He has
Muted.
in the chat box. He has two questions. Yeah, so can I answer them in the
Yes,
order
yes.
that which they have appeared? So prior to that, one small question: what lessons have been learned from the past blackouts, and what policy changes have been implemented to improve grid stability? Now, of course, even from the past blackouts as earlier as 2015, we have made changes to not policy changes, like technical changes, like implementing different stability criteria, not grid stability, of course, plant tripping criteria, of course, you can't violate the safety limit. So anything, if it's done, it has to be prior to the safety limits. So prior to the safety limits, of course, you can play, but beyond that, it's not good to do it. Now, changing the limits, tripping limits, not safety limits, tripping limits has been done by using past blackouts as now the scenario of having these power supply to auxiliary power supply to those certain auxiliaries and all those sort of things are being done because of the past blackouts, of course. Now there is, of course, costs are involved. Now, I'm sorry, wait. Now, what is the total of auxiliary load? Now, during the normal operation, it takes about 25 to 30 megawatts per unit auxiliary loads. it appears that if the feedwater pumps and the condenser pumps are made available running, then the power plant could operate without shutting down. Yes, but it has all its auxiliary systems not made available without tripping them. Now, these pumps should not disrupt themselves. That's the way. If you manage to disrupt it, even though you can start it again, it will take time. So not available. It's not are made available. It should be revised as not disrupted. Then the power plant could operate without shutting down. Actually, the power plant would shut down, but you can resume its operation or restart the power plant soon. What is the time taken for hot start of the power plant? It's depending upon the condition of the power plant. Now you see, of course, the hot start of the power plant, it takes minimum amount of time, maybe 5 to 6 hours, because all the auxiliary things, the temperatures has already reached the levels that needs to be there. I'm sorry, and we don't need to. Most of the expansion of turbine, the boiler, and the steam drum is already there. So hot start. That's why we can start the power plant very quickly. What is the possibility of having a small coal power unit for auxiliaries alone? Small coal power unit. Now, you mean running a power plant for auxiliary supply, right? So that is what is being looked at the moment. Now, but the problem is now for auxiliaries to connect from a small power unit. So this small power plant, of course, will have its own set of problems as well. Now, problems means it will have the same sort of reliabilities, or when it is being connected to the grid, that means that still that coal plant or is any plant will have the same sort of grid instabilities, and maybe for frequency changes and all those kinds of things. So it's the same as having a 6 kV auxiliary supply. What was the range of spinning reserve at that blackout time? Now, I'm sorry, I am not in a position to answer that question because I simply don't have enough detail about spinning reserve at that moment. You probably have to direct it to the system control center, central dispatch center. Is there any correlation of increasing solar generation and power blackout? The same answer goes to the as the earlier one. Now, increasing solar, whether the cause of the blackout is increasing solar generation, I think the report of the blackout incident is still yet to be announced or published. So if the report gets published, we'll see what will there in the solar generation. What are the challenges associated with constructing a secondary unit, such as a boiler or other equipment that cannot function during an emergency situation? Right, no? To immediately re-energize the plant while simultaneously facilitating the cooling of the primary equipment. Now, this means that you have a standby unit available, ready to be supply power, but still a unit such as large as coal power plant, keeping it in standby mode, I think is not a good idea because of the costs involved. Now, keeping standby is somewhat costly for an boiler and equipment, right? So you have to, of course, keeping ready means that you now firing the boiler takes time. After firing, it takes about 5 to 8 hours to synchronize it to the grid. So if the other standby unit needs to be ready during an emergency situation, that means it has to be fired. So that's an not good condition. And of course, the situation of employing a diesel generator is being looked at. Is that pump storage hydropower plant is one of the solutions that considering CB for avoiding Norochchole tripping. Now, even with having high pump storage power plant is not a solution avoiding Norochchole tripping, but a solution for grid stability, so that Norochchole tripping won't be there, or any of the power plant won't be there in the first place. Now, when you have the pump storage hydropower station, you can of course make the make the grid much more stable, so that a synchronous generator is connecting to the grid, so that ultimately it will provide more inertia to the system.
Nirmal,
Rupturing of
being
dam.
a mechanical engineer,
Yes,
my proposal to you, this may be very
yes.
naive, just to have a quick start diesel engine for the auxiliary power, then this would have been avoided. Am I right, or am I grievously mistaken?
Yes. Not necessarily, but the problem is that when you stop any auxiliary equipment, in the middle slide, I have shown you that the priming of the pump, the lubrication oil, all those things will not be there. So to prime the pump, it takes some time. Now that's the problem even with the startup of the diesel generator. Now it's being carefully being looked at, because now what are the methods of quickly priming the pump or quickly priming the line so that we can start up quickly. Now, all the line, maybe you have to have some sort of design changes as well. Now, if you add some more, maybe let's say some more filling locations, so that you can quickly fill it up, avoiding line venting, or maybe closing some converting some manual valves to fast acting valves, or maybe even having along the side the filters and all those kinds of things has to be operated in an emergency situation, in emergency power supply, because now these things has to be closed and sometimes lines has to be filled. So even with it's not a simple power problem, right? So whole lot of mechanical things has to be prepared. You sure know how to the starting of the pump is quite serious issue, right?
It's a complex operation.
So
Now, Nirmal, Dr. Tilak Simalapiti has raised his hand. Dr. Simalapiti, over to you.
yes, sir.
Thank you very much, and good explanation, Nirmal, and thank you for volunteering to explain this to this large audience. So it's only a comment and not a question, that this problem has been there ever since the power plant was connected to the grid, and it has happened many times. It is not that it has not been studied, and the impacts and the solutions and the options are very well documented. It's only that there were many constraints over the last decade. The power plant is 10 years old. There were many constraints, including financial constraints, that prevented the solution being implemented. So, of course, the recent blackout and what happened to the power plant became another reason to examine and make final decisions on the solutions. So if it is a fast cutback situation where the power plant moves to house load, then obviously without any disruption, if there is a source of auxiliary power, it can be switched on, synchronized to the 6 kV bus bar of the power plant, and then the power plant can be brought down to a safe shutdown so that it remains hot to be restarted and loaded when the grid comes back. So that's of course an easy solution. The second one is what Nirmal was explaining to you. Even if you have on-site auxiliary power source, still the fact that particularly the feed pump and the cooling water pumps have tripped, getting those pumps back in operation, even if you have auxiliary power on site, is a complex operation. It takes time, many things to be checked, priming, etc. But it still gives a better chance of saving the power plant from going through a rupture disk situation, which will put it out for 4 days, as we saw this time. So, of course, the final decision will be made in the coming weeks as to what the auxiliary power source will be. But definitely there will be an auxiliary power source adequate to keep the minimum auxiliaries in operation. So until the grid comes back, or to take the power plant to a safe shutdown, so that when the grid comes back, it can be brought back in 4, 5, 6, 7 hours, depending on the stage it is when the grid is restored. So of course, all these cost money. So we have to consider it to be an investment on the reliability of the power plant, the most important and the largest power plant in the grid that keeps the grid very stable at other times. With its very high inertia contribution. So it helps to keep the grid technically stable, and it also helps to keep the grid financially stable as well, because it produces electricity at a price that we can talk about and not being as exorbitant as other oil-fired power plants in the grid. So that's only the remarks that I would like to make, and thank you.
Thank you, sir.
Okay.
Harsha sir, can
Yes, sir.
I keep on answering the
No,
next
I think
questions?
you have answered everything. Are there any more left?
Yes, there is, and rupturing of diaphragm is necessary. Is a necessary condition in full load rejection. Now, if you don't manage to run the cooling water pumps, of course, definitely this rupture disk will be the diaphragm will be ruptured. Small coal unit dedicated to station supply. Now, I think I have answered that question. Is it necessary to alter, augment power distribution grid of Norochchole power plant to overcome continuous shutdown? I'm sorry, I don't exactly get that question. Now, seems like this is the grid has its own limitations. Now, the Norochchole coal power plant was made that the generators and all those equipment are in tally with this distribution grid, not the power grid, with the power grid. Now, continuing shutdowns means I don't think that. So if the power
It's
grid
okay, Nirmal. We can skip
is
that
out of,
question and go to the next one.
yes,
The
yes,
last one.
Isn't pump storage is supposed to peak the demand dispatch? How could it be supporting a frequency control issue like what happened on recent Norochchole breakdown? Now, it's not necessarily that it will stop the Norochchole. It's tripping, of course, not a breakdown, it's a tripping. Now, what it does is it will provide a solution so that many renewable energy power plants can be run when they are available, so that in the meantime the pump storage will come into play so that we can get maximum amount of renewable energy from the grid, so that we can self-sufficient our power system. So pump storage is going to support the peak demand dispatch, because now if there is a peak demand, so of course the pump storage power plant can run, and in the other way around, when the renewable energy power plants are available, because to its own intermittent nature, you can run the pumping mode so that you can use it to store water, so that in a later stage, at particularly peak demand time, you can use it to generate electricity.
I think
So I think
you
that's the
yes, the last question, I think. And
yes.
we have overused the time by 10 minutes, only 10 minutes. So that is more than good enough. So, Himashi, is there any closing remarks by someone?
No, so we could wind up the session if all the questions have been answered, and if
Yes.
there aren't any
And, yes, I
raised.
take this opportunity to thank Nirmal and his team at Norochchole for keeping our lights on, especially amidst the harshest criticism you can get as a power plant in the country. Norochchole is in the top of the list, but we know how hard you work. I have my own colleagues, they are working day and night, and our tribute to them. I would like to mark my tribute to them for keeping Sri Lanka going. And we wish you success in all your endeavors, and also lesser number of grid failures in the future. And thank you once again very much, and have
Yes.
a peaceful and good night, everyone. Thank you.
Yes, once again,
Thank you.
so a big thank you to the presenter and the moderator. And with that, we would like to wind up the session for today, and we hope to see you in another insightful EMF in the future. Until then, good night and have a pleasant evening. Thank you.
Good night to all, and thank you for the opportunity as well.